Okay, hi everyone. Welcome to section. Here's the QR code for today. If you want to go ahead and scan it and fill out the form.
I haven't done this in like 5.
Hmm.
Yeah, I keep forgetting to.
That's okay. Also, this outfit. Yes. No, love.
Literally last minute put together because I woke up like 20 minutes before class started. I was like,
No. Amazing. So let me touch base with y'all and let you know where kind of I'm at with things. So after my section on Wednesday, I was like, I'm not feeling good. I feel lightheaded. And I went home, had a 102 temperature, had to cancel all of my 4th of July plans, and then stay home and rest. And then my fever went away at like 6 p.m. last night, and then I've been totally fine. So don't know what that was. Don't know what was trying to kill me. But here we are. And so I just want to let you know, yes, one thing that you will know from the section notes, or you might have noticed, is it says 2023 by it because I did not really update these. Like I added a QR code and didn't do any of the other changes I wanted to do. And that's because I was fighting for my life. But again, I woke up today and I was like, oh, I guess we're back to normal. Cool. But also, if that means that you want to keep a little bit more distance, totally fine. Totally understand. So, did y'all all see my scary announcement?
Yes.
Cool.
We read it on the walk.
Oh, okay.
I don't know who we.
So, yeah, it's a lot. It's intense. The message from the fast professor. So the year that he sent that message out, he sent it out with no other context. It was just like, do these steps for the practice exam, and then had that, and then end of announcement. I was like, oh no, that's not good. But I do like the intensity of it. I like that it's like, hey, don't screw yourself over for the exams, essentially. With that, the other thing is, you see the box in the back of the room in front of Reese? No, Charlie? Yeah. Charlie. So that box has the practice exams. So if you want to go and grab a practice exam A and practice exam B from that box, go ahead and do it now. They're practice exam A and B. Even if you're a tablet user, I recommend getting a print copy because your exams will be print. There are also extra challenge problems over there if you want to grab them. We probably won't do them this week, again, because it's just a weird week.
Are the challenge problems in PDF?
The challenge problems?
The extra challenge problems?
Yeah, the PDFs of them are already posted. Yeah. And for the people that just came in, you're grabbing printed practice exams from the box over there. So make sure to get the printed practice exams. It's different. So like on a challenge problem, we'll give you something a little bit outside of your comfort zone or push you a little bit further than what you've seen before. On the exam, it should be similar to something you've seen before. Similar to the challenge, like once something appears on a challenge problem, then it becomes fair game for an exam. But like the level of newness that you are to a challenge problem is more than would be the newness for an exam problem. Does that make any sense? Yeah. Okay. Yeah.
Do you, can I ask if you account for checking over in the exam time? Or is that just taking your time but not really?
I was gonna say just like don't check, but like that's bad advice, I guess. I don't know. This is gonna sound horrible. I'm like don't check my work on it. Like, well, just because like.
So you're smart.
No, but every time I've taken a chemistry test, I've known what I did not know. Like I've been like, oh. I'll give some time budgeting advice in the exam review. I'll talk about how to kind of break it down.
Would you say it is 10 minutes per question, or like is it like 8 to 10, or like 5 to 10? But like,
I break it down. Some of them are more like 5-minute pages. Some of them are more like 15-minute pages. Yeah. Okay, so let's talk about what section's going to be like today. So, the first part of section, I don't know about y'all, but lecture 3, if I was in your position, that's the lecture that would have stressed me the most out. Because you go from 0 reactions to a bunch of reactions all at once, and reactions aren't really a thing that y'all have had practice studying. Like, for a bio class, memorizing vocab and facts, y'all know how to do. For a general chemistry class, doing the kind of math problems of the Gen Chem class, y'all know how to study for those and do the practice. Reactions are just a different beast. There's like a lot of visual information, and it feels very spread out. So we're going to start off for the first roughly half of lecture, or section, with my little TED Talk on how to study reactions. Then after that, we'll talk about some of these reaction families that I kind of group them from the reactions of lecture 3 into little families. Cool. So let's jump into things. So the first kind of big idea is y'all need to know how you're going to be tested on reactions in order to effectively study for them. So let me introduce, quote, quote, a line reaction. So line reactions are things that look like this, where you have some sort of starting molecule, then you have an arrow, and on that arrow you have some other reagents, solvents, reaction conditions, something like that, and then you have a product molecule. Every reaction that we give you in this course, you will be given a line reaction for it, and then some of them, or I will say most of them, you're then given like a full curved arrow mechanism of it. So line reaction and mechanism are the kind of basic parts of a reaction that we would give you in this class. And so then if we were trying to be like, how do we test y'all on the line reactions, we turn them into what are called box problems, where we just put a big box over one part of the line reaction, and you have to fill it in. So here, the classic example is we give you a starting material, and we give you some reagents in the arrow, and you have to predict the product. But we could also put the box over the reagents and give you the starting material and products, and you have to fill in kind of what's in the middle. And then the kind of harder one is if we give you the product and the reagents, thinking backwards and getting what is the starting material that we had. So 1 page of your 9-page exam will be box problems. Now, one thing, we are only grading the structures and what you write in these boxes, right? So does it seem likely that you should be thinking through the whole mechanism for these questions? No. So we're going to keep that idea, like do a little forget-me-not, and save it for later when we're studying the reaction, that we need to be thinking about how to do these reactions without doing the full mechanism. Just mentally, how do we get to the products? Yeah. Verb.
okay, sorry.
So the second type of question is a mechanism question. So this is the most detailed type of question that we can ask about a reaction, where it's going to be write the full curved arrow mechanism that happens. This is explaining how a reaction happens, whereas up here it's kind of like what has happened or what will happen. So most detailed type of question, we could even ask you to identify HOMO-LUNA interactions, but this is like drawing all of the arrows. I kind of divide mechanism questions into 2 camps. One is a known mechanism question, and that is where you are just regurgitating something almost verbatim from the lecture slides, where you're drawing the exact same arrows, nothing new, nothing weird. And then, don't freak out, there's a new mechanism type of question, and we will only give you something new if it's very, very, very similar to something you've already seen. And we will typically spell it out of like, this is similar to the thiolate mechanism. Like, we will not try to be coy about it, but it will look a little bit less familiar than the ones where you're just straight up regurgitating arrows. I think on the actual exam, you're only going to have known mechanisms, but the thing I will tell you, one way that we can make a known mechanism question harder is by doing more than one at a time. So we could do like 2 or 3 reactions back to back to back, and you have to do the mechanism for it, and that's a way to make it a little bit harder.
Will
Yeah.
you not tell us more than one?
I mean, we will draw more than one thing on the arrow, but it's kind of, if we give you the line reaction, you should be able to figure out what reactions are happening based on the line reaction. And for a mechanism question, we will always give you the line reaction. Yeah, and so you will fill in all the details of the curved arrows. So we had box problems, mechanisms, and then we have the last type, which you all don't even know about, and it's like the Thanos bad villain type of question. It's the hardest type of question in the class. So these are synthesis questions. What we will do is we will give you a starting molecule and a product molecule, and then say, in 10 or fewer reactions, go from the starting material to the product. Now this is not one that you could do. Like this is one that uses some reactions that, like this is like a exam 2 synthesis. So like you don't know this reaction yet. This is just for an example what a synthesis would look like. But essentially it's like doing a bunch of line reactions. Of like line reactions, intermediate, line reaction, intermediate, line reaction, intermediate. And so to do this type of synthesis thing, you need to have kind of zoomed out from all the reactions to kind of pick what is the right reaction to accomplish the goal I want to accomplish. And this, like, maybe I'll just phrase it this way. I think that you can imagine how well you will need to know these reactions in order to do something like this of synthesis, of putting it all together. Like you will need to know these reactions kind of inside out, backwards and forwards. Now, the problem set has a synthesis question on it. Both the practical exams have synthesis questions. And the synthesis question on the first exam, I believe, is 6 or fewer steps. So it's not going to be a 10 or 12 step one, so that it won't be nearly as intense. But synthesis, she's a beast. She's the hardest type of question that we ask in this class. But there will be one page of the exam for this first exam, a synthesis. I think there will be 2 on the second exam. 2 or 3, I'm not sure. Also, I hate to say it, those of you who had the choice between 17 in the summer and 17 in the fall, synthesis is not in 17 in the fall. Synthesis here, well, it's because this class should prepare you to go into 27, or if you want to go into Chem 30 and do the chemistry major version. And synthesis is in the Chem 2030 sequence, so.
So if like we're doing the peer tutoring, and the peer tutors have taken 27, then who does synthesis?
Probably not. Yeah. 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 There's one thing I want to say, but I don't want to commit to it. So I'm going to say this, but I didn't really say this. One thing I'm going to try to do next week, probably next Tuesday, is I'm going to try to record a video of me talking through all the synthesis problems on like the PSET and the practice exams, just to kind of like verbally talk through them and like how I'm thinking about it to help. I didn't say that because I also was like, I'm going to upload the annotated versions of all the section notes, and then that hasn't happened. And then, you know, some small microorganism tried to kill me yesterday, and so, you know, we can't predict anything, but I'm going to try to do that. Cool. So these are the main ways that we are going to test you on reactions. I have some general advice here. One is you should be studying reactions as you are doing practice and doing the problem set. If you wait to fully study the reactions and then do the practice, you likely will not have enough time. And so I encourage you to use the practice to help you figure out what you do and do not know, and to kind of organize your studying. The biggest challenge that I see organic chemistry students face in the class as a whole is how to be handed 10 new reactions and to take them in and digest them and understand them and make them part of their kind of arsenal of reactions to do all these things with. Like, that is the big challenge, because lecture 5 onward, each lecture we're going to give you 10 to 15 reactions. And it's just going to be more reactions until the end, and that's basically the whole course. Lectures 1 through 4 had some like hodgepodgey things of like stereochemistry, MO diagrams. After this, it's only reactions. So the faster that you can develop this skill of taking new reactions and kind of internalizing them and learning how to study them, that's the faster that you're going to kind of succeed in the second half of this course. Another metaphor that I really like is the idea of you have your kind of chemistry toolbox of all your reactions. And if you have all your reactions thrown in the toolbox and it's really hodgepodge, then each time you need to like reach for the wrench, you have to dig through all of the reactions that are in there. And so the other thing to be thinking about is how do we organize these reactions into clumps that will be easier to sift through? And so I use this idea of reaction families that we'll get to in a little bit. But just thinking about, okay, I not only need to know each of these separate reactions, I need to figure out ways to organize them and group them together. Questions so far? Okay. So, I'm about to introduce this method for how to study a reaction. So I picked the reaction that's hardest, the one that's the longest from lecture 3, the acetal formation reaction. If you're a tablet user and you are writing on the tablet here, you can annotate this along with me. If you're not a tablet user, I would say pull out your lecture notes and go to the page that has the acetal formation mechanism, because we are going to be doing some annotation here as we try to study this. So, the big premise of this method of studying reactions is we need to study the reactions at different levels of detail. So maybe let's start off with the most detailed level, which is the full mechanism. Each time there's an arrow, we need to understand why that arrow exists. We need to understand HOMO-LUMO interactions. We need to know exactly why each step is happening rather than I'm just copying this down. So that's kind of the full mechanism. And again, this is important, but if we only study this way, then it's going to be too time intensive and we won't be able to answer some of those questions like just predict the product in like a line reaction. So we are going to go through and we're going to kind of analyze each one of these steps for the full mechanism. And as we do that, we're going to do the second level of detail as well, which is mechanistic logic. So we are going to try to summarize and label each step in a few words, just to kind of translate curved arrows visual stuff into words. Because like that may seem like really basic, but it can be a very powerful tool for noticing patterns and for studying it. So let's try that with the mechanism here. So this first step, does anyone want to give me a kind of like few word summary of what do you think that, how could you summarize this step? Yeah. So, you're very close. But there's a better name that we have for this than a nucleophile electrophile. What's the better name that we have for this? Acid base. And what do we call it when we just add a proton or something? Yeah. So I might call this protonate the carbonyl. And I'm not even writing out carbonyl, I'm writing C double bond O. So protonate the carbonyl. Okay. Why do we do that? Yeah, but that's why do we do the reaction in acid? Like why? Why? Yeah, why? That's fine. Yeah. There's a better reason for why. You got there, you got there, you got there. Why else, specifically for this first step? Why do we do this first? Because that explains why acid's important later. Okay. Great. So, we make the pi CO, and maybe I'll say, actually, I'm just going to say make the carbonyl a better electrophile by lowering the energy of the LUMO, which is the pi star CO. So it's the thing of, remember our low energy trifecta in our MO diagrams where like electronegativity, charge, and S character all kind of lower the energy level of a molecular orbital. So when we have a positive charge on this carbonyl, that's going to lower the MO from pi star CO being here to kind of pi star CO being down even more. And since it's a LUMO, we want our LUMOs as low in energy as possible. And we would want HOMOs to be as high in energy as possible. Yeah. Because it gives a positive charge on the oxygen, and that positive charge lowers the energy level. Okay, So how would we summarize the second step? Yeah. Yeah, I'm going to phrase it as alcohol, nucleophile, attacks, carbonyl, electrophile. Great. What's the HOMO-LUMO interaction? Yeah, lone pair and oxygen. Pi star CR, yeah. No, you're good. Great. Okay. Cool. So I'm going to group these next two steps together as one big thing. And when we have something like a deprotonation followed by a protonation, we give it a special name. We call it a proton transfer. So did Tim use that phrase in lecture? Does that ring any bells? It'll be coming back later, but so the other thing that's kind of weird is I put sol here for something in the solution or the solvent, but I think Tim just actually wrote this out as HOET, another equivalent, goes and deprotonates it. Sol is just like a generalized version of something in the solution is going to act as a base and grab this. Some classes would use like a little B here for saying something's acting as a base. This notation essentially means we don't really care exactly what's grabbing the hydrogen, but we care that something is grabbing the hydrogen. But if you just want to write the HOET, that's fine. If you want to write sol, that's fine. So we have the proton transfer. And to understand why this proton transfer happens in this reaction, let's look at the next step, okay? So can someone summarize this next step? Lone pair push. We're going to lone pair push off water. Now, I think Tim downplayed this in lecture. The lone pair push is the cinematic moment of the reaction. This is like 4 friends in college sharing an apartment, and the apartment is this sp3 carbon. And then Clarissa over here is like, Brenda, I've had enough of you. I'm going to pack your bags and push you out of the house. And it's very dramatic. Can we all agree that's very dramatic? Thank you. So the lone pair push is a moment of like high drama in the reaction. And when we do that, we are breaking a sigma bond, and breaking sigma bonds is kind of a big deal, especially sigma bonds to a carbon. So we're lone pair pushing off water. And then what's the HOMO-LUMO interaction here? Go ahead. Yeah, and how do you know that it was the sigma star CO? Yes. So we know if we put electrons in antibonds, the bond breaks. So if we know that we have broken this bond, we know that we must have put electrons in the antibond. Great. Okay, so now with this in mind, let's back up and try to figure out the why of the proton transfer. So why do we want this OET to be neutral here? Why did we want to deprotonate it? Yeah. Or so that it becomes a better like nucleophile for the lone pair push. Yeah. So we want to kind of set up the OET for the lone pair push because it needs to have electrons on it to do that lone pair push. If it's a positive charge, it's not going to want to push electrons away. And then, why did we protonate this OH? Yes, and. So, let's say we didn't. Let's say we just had this as OH. Boop. Then when we kicked it off, it would be OH minus. Yeah. So it's kind of like when we kick something off, we want it to be as stable as possible because then it'll be easier to kick out. Like in my little roommate metaphor, let's say we're trying to kick out Brenda from the apartment. If Brenda's mom just died, it's going to be hard to kick it off. But if you have just helped Brenda like pack her bags and said, hey, you're going to find it out there. You're going to find success and love and all the things. It's so much easier to kick Brenda out, you know? So that's kind of what's happening with the molecules. Here, you want to protonate this so it will be neutral and stable when you kick it off. In other words, we need to make the OH a better leaving group. And a leaving group is just the thing that leaves. And we will abbreviate it as LG sometimes. Cool. So we have the proton transfer lone pair push. Step 5. How should we characterize this? Yeah, it's deja vu. Look at this. The exact same arrows. Exact same. Exact same homo-lumo interaction. Exact same. So I'm just going to copy this. And paste it right here. Great. And then our last step, how would you summarize this?
Another proton transfer?
Well, this one is just a deprotonation. To do a proton transfer, you need both a deprotonation and a protonation together, kind of back to back. So this one, I would just say deprotonation. Okay. And then, why do we do that? Why do we deprotonate it? Yeah, that's okay. So a proton transfer is specifically when you have a protonation and a deprotonation step, separate steps back to back in a reaction. Because in any acid base, you have something that is going to be getting a hydrogen and something going to be losing it. But it's kind of about what's the main character here. Here, this is the main character and it's being deprotonated here. And this one, it's being protonated here. So it's kind of like a grouping of two steps, two acid-base reactions happening. One deprotonation, one protonation, all happening kind of to that same molecule. That's what we call a proton transfer. Yeah. Why do we do this deprotonation at the end? Yeah, so to just make it neutral. Great. So we've just kind of done this full mechanism, like full detail level. This is the most detailed level that you would need to know a reaction at. But that's a lot, right? So let's talk about how to kind of generalize this and kind of take a step back a little bit. So all of our little summaries. 1, protonate carbonyl. 2, alcohol nucleophile attacks carbonyl electrophile. I'm just rewriting this, sorry. Proton transfer. Alcohol nucleophile attack carbonyl electrophile. Or I missed one, sorry. That's step 5. Step 4 is lone pair push off water. 5. And then 6 is deprotonation. So, from just this word of like protonate carbonyl, me mentally, I know I could draw arrows for that. Like, I know that that corresponds to this. For alcohol nucleophile attacks carbonyl electrophile, I know, okay, carbonyl, alcohol, I know I'm going to be doing these arrows. And I think a lot of y'all know that as well from these words. And so this is a really nice, concise way to take a bunch of visual information up here and now make it a short list. And y'all are good at memorizing lists. Y'all can make flashcards. You've had to learn lists for many other classes. And so this is just something more compact way to think about it. And then if we kind of think even deeper about the mechanistic logic at play, which of these reactions would fall under the category of an acid base? First. What else? 3, the proton transfer, that's acid base 2 times. And then 6. Those are all acid base. You could do acid base arrows last week with PSET 1. So y'all know how to do acid base arrows. Then the lecture 3, the new kind of big type of arrow was alcohol nucleophile or some sort of nucleophile attacking a carbonyl electrophile. And then the only really other fundamentally different type of arrows was the lone pair push. And so if you kind of zoom out a little bit, you see all of the arrows in this reaction, and really all of the arrows in every reaction that we taught you, are really just these 3 kind of basic steps of a lone pair push, a nucleophile attacking carbonyl, or an acid base. So almost any arrow that you draw on the exam should be one of these. Cool. Questions so far at these kind of most detailed levels? Yeah.
So the summary you just made, is that just for these 2 information?
Yeah. So I am showing you this as a process for studying this reaction, but then when you go to study other reactions, you should make a similar list. And those lists will have similar steps, very similar. But this exact sequence of steps are the steps that characterize the acetal reaction. Yeah. Other questions? Yeah.
This is gonna say, but is it like difficult for this to be kind of like intuition, where you know how it's gonna go without having seen the reaction?
The thing is, we're never going to ask you, like, without having seen the reaction first, how is this going to go?
So like if we forget, let's say in one of these, yeah, we can't figure it out.
Sometimes you can, sometimes you won't be able to. It's a thing of like, the more you practice it and the more you feel comfortable with these reactions and these steps, the easier it will be to figure out what happens in a new and different situation. So that's something like Chem 27, they're going to be doing things that are a little bit more unfamiliar on test questions, where it's just you have to extend your kind of chemical logic and reasoning to something new. But we're going to do less of that. Yeah. So it's kind of the thing of you want to be understanding how the molecules react generally, but in order to do that, you need to have a standard of comparison of reactions that you know that this is how it works. And so until you have a body of reactions where you know how all these work, it will be nearly impossible to just intuit what's going to happen until like you have more. So like right now when you're learning your first reactions and the first like several reactions, the first several dozen reactions, it's kind of just memorizing this is a reaction, we're telling you what happens, and you should make sure you understand why each step happens. But the developing kind of chemical intuition, that's the thing, that's the goal that we're aiming for. But the memorization is kind of first. Yeah. Cool. So let's zoom out and do these kind of higher level skills. So the way I tend to put it is you need to study line reactions as connected but fundamentally distinct pieces of information. Because all of this of focusing on the actual atoms and the curved arrows is a lot of detail when sometimes you just need to write the product. So one of the first things that you should do when you do a line reaction, studying at the line reaction level, is just generalize the functional groups involved. So what's this functional group? Aldehyde. And we could also put a ketone here, it would react the same. So ketone or aldehyde. This one? Yeah, alcohol functional group. And we could do any alcohol. We could do methanol, ethanol, propanol, butanol, any of the other alls. I don't know. And then what's this functional group? Acetal. It is the acetal formation mechanism, so it would be weird if it wasn't acetal. Cool. So this kind of helps for us tag when it would be relevant to use this reaction. So, like if I saw an acetal in the wild, like on a box problem or on a mechanism or whatever question, you will only know one reaction that forms an acetal, and it is this one. And so that's just kind of a tag for you to know, oh, okay, this is what I need to do. Or if you have something that has a ketone aldehyde and an alcohol, then that should flag, oh, okay, this is either going to form an acetal or the hemiacetal is the other one that does this. And then the only difference is whether it happens in acid or base. So functional group analysis is really important. The other thing for working at the line reaction level is doing something that I call a fake mechanism. So a fake mechanism is just tools for a non-chemist to just write the correct answer. So a fake mechanism will include things like erase this, draw this. Like it is very rudimentary. How do I draw the correct product? So if we look at this, and I had to kind of come up with a fake mechanism for this, I would say step 1, erase the carbonyl. So just kind of do this. And then step 2, it would be, well, this is an alcohol, right? And this alcohol could be anything as like ROH. And that R group could be a methyl, ethyl, propyl, whatever. So it's kind of like we only care about this part, right? That's what winds up in the actual product. So here for OET, or for ethanol, we would have OET wind up there. So for any kind of general one, we would add 2 ORs in its place. And again, this is just a short trick for you to write the answer without having to think through the full mechanism. So with this in mind, can you try to write out what the product will be of this reaction using the fake mechanism? It's another acetal reaction, but I've just changed the identities of the molecules. So the first step here, I just erase the carbonyl, so it's erased. And then I add 2 ORs. And here my R group has 1, 2, 3 carbons, so I make sure I have 1, 2, 3 carbons. O, R. So much faster than trying to do the full mechanism. And like this is the only thing that we would grade you on for that type of line reaction question. Just did you draw the correct product? So that is kind of working at the line reaction level of detail, where it's not all the explanations of the why, it's not all the curved arrows, but it is tools for you to answer specific types of questions. Cool. So let's zoom out and do the final kind of like higher order thinking here, which is looking at reaction goals and purpose. So the reaction purpose is essentially, why are we teaching you this reaction? Why is this reaction part of the course? What is its purpose as a reaction that someone did their PhD on 200 years ago or whatever? Generally speaking, the purpose of most reactions is to go from one functional group to another. So I would say that for this reaction, its purpose is to, trying to change color, reversibly interconvert between a ketone / aldehyde and an acetal. So that is the purpose of this reaction, to take us from a ketone aldehyde molecule to an acetal molecule and just change out that functional group. Now, goals, on the other hand, are much more concrete. Like, like SMART goals of like plannable, actionable, or whatever the acronym is for like setting good goals. Um, Goals for a chemical reaction include what bonds do we need to make and what bonds do we need to break. So, what are some bonds that we need to break? Yeah, so we need to break these bonds, right? So we have the pi, CO, and the sigma, CO. And then what bonds do we need to make? Yeah, these two sigma COs, yeah. So these help us, especially on when, like, your question where you were like, what if we like forget halfway through or something? How likely are we to figure it out? This is where goals can help you, because each of the arrows drawn in the mechanism should be in service of accomplishing these goals. So let's go through real quick and say, where do we meet these goals? So does this accomplish any of our make or break goals? No, but it sets us up for this. So here, what make or break goals did we do? So we broke the pi CO and we made one of our sigma OETs. I'm gonna do a little highlighting. Break, make, break. Okay, these steps, do they do any direct make breaking for our big goals? No, but they're setting us up for this step. And what goal is this accomplishing? It's breaking the sigma CO. So with that, at this point in the reaction, we've accomplished both of our break goals. Okay, and then in this step, are we accomplishing our goals? Yeah, we're making our second OET. And so we can see how each step in this reaction is connected to our chemical goals of what we need to make and break, or it's setting us up for that. And so that's where, if you understand kind of the goals of the reaction, and this you can kind of figure out just by looking at a line reaction. It's not something you need to memorize per se. This is what can help you and guide you of everything has to be kind of working towards those goals. So with that, we've kind of beat this reaction to death. We've done a lot with it. But really what I want you to get out of this is like there are very different ways that you can view this reaction at different levels of details. And the more ways that you are looking at a reaction, these are tasks that you can do that are helping you to study the reaction. And so again, I wanted this to be kind of like this is a process of understanding a reaction each time you get a new reaction to go through and work on each of these different levels. And I've done this one with you. The rest you will need to do on your own. But to help you out, since this is new and scary, I have made a summary sheet. So the summary sheet, the acetal reaction is the one that we just had over here. You know our 6 steps where I had the mechanistic logic, that's up here. I've kind of just done that for all the other ones. And so I've summarized all the steps. It doesn't have all the curved arrows. And then I've kind of put stars for like what the important kind of side notes are for the reactions or commentary. I will also say this is a trap. So if you just use my review sheet and you don't have to make the review sheet on your own and organize it yourself, you're not going to be learning it as well. Like you should still make your own study sheet, but I wanted you to see what a good study sheet looks like and how organized it can be and kind of compartmentalized so that you have that to study with. Yeah.
Does that include each reaction we studied for the test?
Yeah.
That's all of them?
This is pretty much all of them. The only thing really that I can think of that isn't on there is the thiolate reaction, which I include here on the section notes. I generally try to make the section notes pretty comprehensive, but like don't hold me to that if there's not something. But that's the only one I can think of that isn't on here. So this is pretty much all the reactions. Yeah.
I just see some reactions as universal and some are universal. How to memorize which chemical reactions are universal.
So this is kind of a broader note. The way I've divided this up is in terms of reaction families. So in lecture 3, there were 3 reaction families to me. One of them were these organometallic reactions. One was the hydride reactions with the sodium borohydride, lithium aluminum hydride. And then one were these carbonyl additions that would go from like a carbonyl to a hydrate or hemiacetal or a cyanohydrin or whatever. This family is reversible. These families are not. And that is the thing of like the reversibility of a reaction. Again, once you have more experience with chemical reactions, you'll be able to see which steps are reversible or not. We're not going to ask you that. It's going to be a thing that we will explicitly tell you if it's reversible or not.
For the reversible ampersand levels are shorter.
Yeah.
So you put so we need to draw for the mechanism.
Y'all do not. I've just drawn this to say, hey, this thing is generally going to be more stable than this one if it's pointing this way. Or, hey, this thing is going to be generally more where the equilibrium favors than this one. If you just did this, that's fine. Yes. Yeah.
For each step of the mechanism, does it matter if we draw single arrows or double arrows?
What do you mean?
Like when we did the mechanism of like when we're going from one pivot to the other, like is it still reversible all the way through?
Oh, yeah. So if a reaction is reversible, every step is reversible. But we are saying that we are not going to grade you on whether you do this or if you just write it as this. Yeah. Yeah. Cool.
What if we find different ways to get to the product? It's just like
I mean, generally, the different ways that students provide are not correct. And we can talk about in specific cases why something is not correct. I mean, if you did find a different way that was 100% completely correct, you would get points. It's happened very few times. Yeah.
Some of the steps sometimes can occur in a different order. If you mess up the order, is that
Messing up order is like a smaller deduction. But generally, the order matters in terms of the steps. But with that, thank you for coming to my TED Talk. This, like, started doing a version of this my first summer, and this is the one that I feel like is the most helpful for y'all for like how to kind of approach studying these reactions going forward. The next part of section is going to be a gear shift. It's going to be more like a normal section where I present things and we do some practice. So why don't we take like a 2 or 3 minute break to just like stretch your legs, kind of change up the scenery. Yeah.
Do you guys like one lecture from the first 4 weeks?
Why can't I remember your name? Don't tell me. Don't tell me. Sarah.
It's okay.
Kendall.
Yeah.
Works. Okay. Yeah.
Is there like out of 4 lectures more than you make more like focus on the I feel like low-key this
I mean, so this one is going to be 3 questions out of 9, so it's 33%. But like, that's not a huge difference.
Wait,
I
can
mean,
I
I feel like a
Fire.
lot of section 1 was just
and then I'll just text you.
like view of like judges.
Exactly. Like section 1 will have some questions in terms of like hybridization and like functional.
Like you all are gonna ask us to do like Lewis Jeffers.
No.
I was just wondering, I was thinking of one of the examples, and
Oh, we're not asking.
I have a question. It's kind of like, it's not a great thing.
Yeah.
Is this a catalyst because it removes one step from the reaction? Because otherwise, if we just had H2O, then
Is that how you spell it?
of like cheaper.
Yeah, that's tomorrow.
So
I actually went to Cabot today.
a catalyst is something that's not consumed in the reaction. So if you started off in OH minus, you need to wind up in OH minus.
Alright, last.
And it's because, like, the way that we've done it, we've done this through OH attacking. But you can think of this as this OH deprotonated water and water attack. And then at the very end, you would reform it. The important part here is just you start off in OH, and OH is reformed, so it's a catalyst.
But this OH comes from here, right?
Yeah.
Yeah.
So if we didn't have this,
And the cleanup.
Yeah.
Oh,
It would just be
the
very
reaction
slow.
would yeah. But that would be because like we would have to kind of deprotonate this for that reason.
Well, you wouldn't be able to deprotonate it. It would be water attacking, which would release it. Then this would be OH2 plus, and then you need to deprotonate it and generate another water. Yeah.
Yeah.
Abby does
Just
the
really.
I
I love orange, and then also I love like a full.
I thought this would be too bright, so I like these two. This would kind of
Yeah.
a little bit.
Work.
So this was like the set, and I was looking at this, I was like,
So is this a series?
Yeah, I gotta take a lecture for the one that
This is the metal. This is the metal. So this is it a series one? Is it a
I
column?
did like one dry electrical through, and so I got the seven parts up and
So even though this is
Yeah, it's not like an unlimited amount of times.
because it's a cuts.
It's really taking my time. I figured that out, but I didn't get a 100 after 3 times. Yeah,
It's the exact same. Yeah.
yeah, actually, I was gonna.
I always hate to say it, but like the best way to convince yourself of that is to build it. It's a thing of like truly. I remember being in the stereochemistry lecture when I took it for the first time. And I said, "This is fake.
It's not that.
This is entirely fake."
Yeah. Or it's gonna rain at 8. Oh. Just looking at it.
Well, and then after that, I like bought.
Yeah,
I
we
now
can
have
do it
like
after
3
this.
molecules, like just because I wanted more carbons.
Yeah,
And
literally.
like, yeah, no, it's not fake. It just takes a minute. Okay, you.
Said the first one.
I can help you with that if you haven't started that. I also want to help you once we start together.
Just like saying that song.
That's cool.
I actually
That was
did
gonna
watch the
be
movie.
that's the best part.
I think that is the best part. But I think it's like, you know, like the even British guy who was like, first night fun example.
Yeah.
Even to like the end of the song, when people would react to it.
I haven't
To
watched
do
that.
it.
I haven't watched that movie since I was like in middle school. Or like elementary.
Yeah,
So like I don't know what part you're talking about.
He's like the main villain, right?
Probably. You actually watched the movie.
I'm just sitting here doing that.
That's hilarious.
I'm gonna watch the movie.
Yeah, this is where it's
I was
embarrassing.
looking at this for like 20 minutes. Isn't it?
I'm done.
What's your name?
Did you do anything fun
Kate.
before?
Kate.
Let's see what I do this year. I tried to do something. I walked out to
Oh, the front row.
Yeah. You could see it from like wherever.
Georgia
Wherever
Agadir.
you walk up to it.
Oh my gosh.
Yeah.
Kindle.
Yeah.
Why? Why? Why?
Abby.
Abby, are you don't Ben George? No. What's your name? Daniel, Abby. Okay, next week y'all need to start shaming me into remembering your name because I'm at about like 50% right now, and I need to close the gap.
Okay.
Yeah.
Okay. We're starting.
Shots fired. Shots
You
fired.
want to start next week? We're starting the shaming now. That's how this happens.
So for studying, like I'm good at school. I can memorize facts.
He cares
Sure.
about ketones more than us.
It's a thing of like, it's a very visual memory thing. Like if y'all all wore name tags the first week, I'd be golden. But it's a thing of like, if I can't see it, then it's like, oh gosh, what's going on? So it's more visual memory than, wow, they just don't care. Work. Also, yeah, sorry for the squawk. My cackle is a bit jarring. Okay, so
What? Also, why did we do section 4 before section 3?
it's to keep everything lined up with the lectures. So, like, wouldn't it be more confusing if section 3 was associated with lecture 4 and all the other ones
Why
were?
do they number the sections like that? What are they- how do they
Oh,
order?
because this was the worst week in terms of like, we're gonna have a lecture on Tuesday, then Wednesday, then section. Yeah, it's horrible. I did not want it that way. Yeah. Welcome back. So we are going to start off in the next section. We're going to talk about this family of carbanion equivalent reactions or organometallic reactions. So the purpose of this reaction family is to add an alkyl group to a carbonyl compound. And again, this is thinking about that purpose highest level for a reaction that we talked about before. So I like this little meme of like it's the dog playing with the two tiny dogs, and it's like carbonyl, an alkyl group, and it's like kiss, and just like put them together. So that is what this reaction is trying to do, or this reaction family. So question, why do we not just deprotonate alkanes and make a carbon anion, and have this do the nucleophilic attack like bleh? Why don't we do that? Yeah. pK is like 50. And once we start talking about like bases that can deprotonate something that has a pK of 50, we're in the, ooh, something just blew up in lab today kind of land. And we want to avoid that land as much as we can. So we want something that's going to react like this, but be stable enough for us to kind of do under normal lab conditions. So we say that we are looking for something that's roughly equivalent to a carbanion, a carbanion equivalent. And so any CO bond, for example, where's the partial negative, on the carbon or oxygen? On the oxygen, because it's more electronegative, right? So if we want carbon to have more of a partial negative on it, we need the carbon to be more electronegative than whatever it's bonded to. And so for our purposes, that means that we are going to use a metal, which I'm just abbreviating metal M here. So electronegativity of carbon is 2.55, but most metals have electronegativities of less than 2. So in this bond, carbon's going to be the one that's partial negative, and it's going to be kind of like that carbanion. So that's kind of what we're after. And then our two metals that we use here are magnesium bromide or lithium. And these are kind of first two entries in this family for the reactions. So the magnesium bromide version, that's called the Grignard reaction. Can we say it all together? Grignard reaction. Not Grignard. One more time, Grignard. Grignard. Thank you. So Grignard reaction is the MGBR, and then this one is an alkyl lithium, which that I think makes more sense as a name. Grignard was a person. So whatever the R group is that's on the Grignard or the alkyl lithium is the R group that we're going to add. So if I wanted to add an ET, an ethyl, then what should I put right here? The ethyl that I'm trying to add. And same right here. If I wanted to add a phenyl group, what should I put right here? Great. Experts. We love it. So, few things to know. One, we have a solvent, diethyl ether, ET2O. Now, solvents threw a lot of y'all. Like, I got a lot of questions asking about solvents. So, basically, the solvent is what a reaction takes place in. So this thing, if we just had it alone, it's probably an oil. And this thing is probably a solid. So if I just tried to put the solid on top of the oil and say react, it's going to do a poor job reacting because it's not going to be able to mix well and interact very well. And so we dissolve both of them into this solvent. And that's going to help facilitate the reaction just because they can interact more. They're all like spread out inside the solvent. Now, solvents either can or cannot interact with the reaction. Like in some reactions, the solvent is going to play a role in the mechanism. And in other reactions, it's just fully not. The solvent's just going to be where the reaction takes place. In this reaction, this solvent does nothing other than be a solvent. So it's not involved in the curved arrow mechanism at all. You will draw no arrows related to diethyl ether. But you still have to write it. Because, again, if you did not write it, it would be like, oh, I'm going to put the solid on top of the oil, react, and it would be really poor reaction. Questions on what is meant by the ET2O solvent here? Yeah.
Can you kind of just go over like why we put stuff where?
Oh, I'm about to. So, 1 and 2. That means first step, add this, and then wait and let it react, and then second step, add this. If I did not have these two numbers here, it would be saying we are adding all of this with the starting material into the same pot all at the same time. And that would be bad. Mostly because the Grignard reagent or alkylithium, these are actually very basic. So, if you even had like water, this is just going to go and grab the hydrogen from water, and it's not going to do the attack that we want it to do with the carbonyl. And so that's why we need to make sure that these are two separate steps, because this thing would rather react with our acid workup than react with our starting material. Also, when we have acid workup like this, that's kind of like a weird notation. Different classes do different things. So acid workup, H plus workup, all of these mean the same thing. Some classes, they put literally an acid. They put H3O plus or HCl or H2SO4. Or sometimes you can even just put water for your acid workup. Basically, this is a notation that says we don't care exactly what we add here, but the purpose of it is to add an acid so that we wind up at a neutral molecule. And that's what this notation means. So we will write H plus workup, and you should also write H plus workup on like the questions. You don't need to specify. We don't care. Cool. Oh, and then also the bats. So diethyl ether looks like this. 2 ethyls on an ether. It's like a little auction bat. And then Grignard sounds like a vampire name. And so I think, oh, okay, the solvent for the vampire reaction is the auction bat. Just as a little, like, memory thing. Yeah. Because otherwise it's like, why are the bats here? Okay. So now let's talk about, very quickly, how do we make the Grignard reagent and the alkylithium? We start off with an alkyl halide, and we either add elemental magnesium in diethyl ether, or we add lithium in diethyl ether. This little 0 superscript is just saying that we are talking about elemental magnesium with a like neutral charge. And that's kind of a reverse magnesium ion of like Mg2+. Like this is going to be, this is not going to accomplish the reaction. This is an aqueous environment, whereas this is solid. And so it's just a bit different. Yeah, and this is where I make the note of the Grignard being a strong base. The alkyl lithium is also a strong base. For these reactions, you are not required to know the mechanism. So these you only need to know as a line reaction. And so this could be used on box problems, it could be used on synthesis problems, but you do not need a mechanism for them. But let's talk about the actual mechanism of the Grignard or alkyl lithium. So you will draw an arrow from the carbon metal bond. Do not, I know he did like briefly, he like wrote electrons here, don't do that. Just draw the arrow from that sigma bond over to attack the carbonyl and push up. That adds the R on, and then the metal, the MgBr, the lithium just kind of falls off. And then you have O minus here, and then you are going to protonate that. And this is the step 2, the protonation. And then it's neutral. Doesn't this look like a cute, quaint little mechanism compared to the acetal one?
We'll just do this.
Yeah. Well, this is the thing. Like, I wanted to do the hard one with y'all so that y'all would be less scared. But if I did this, it would make it seem like all of them are that easy. And then acetal is woo. Yeah.
Are we gonna like combine stereotypes into this?
Eventually, but not for exam 1. Yes. So, there's a slight variant of these reactions, which is what if instead of attacking a ketone or aldehyde, we attack an ester? When we attack an ester with the Grignard or organolithium, we get double addition of our R group. So the first thing that you should think when you see an ester, especially for exam 1, is double addition to esters. So can we try a call and response of ester, double addition to esters. Ester. Hi, I have a medium hot latte here for Esther. Thank you, thank you. So let's talk about why this does double addition, whereas the other one only does single addition. So the first step looks exactly the same in the mechanism, but then we get to this intermediate and contrast with this intermediate here from if we just attacked a ketone or aldehyde. This intermediate has this OET, which is a leaving group. And so because we have a leaving group here, we can do a lone pair push and kick off the leaving group. Whereas over here, we don't have anything that can act as a leaving group. Because otherwise, all these things are carbons or potentially a hydrogen. And if we kicked it off, we would have a C minus. That's the Ochem reaction land, or not Ochem reaction, Ochem explosion land of carbon minus. That we don't like that. She's never going to leave. So it's because here with an ester we have a built-in leaving group that came from this OET, whereas here we have no leaving group. When we do that lone pair push and kick off the OET, then we've made a carbonyl, and we're still in this portion of the reaction that we have other like Grignard reagents around, and so another equivalent can come in and attack. And that's how we get that double addition. It's because one of them adds, we do a lone pair push, make a carbonyl, and then another one adds. And then from there, it's exactly the same of protonation for the last step. Cool. Work. Yeah, that's all I have on esters. Now, one question that you might be having right now, which I would be having if I was in your shoes, are why do we have two reactions that do the same thing? Is that something that anyone is wondering? Some yes, some like, I don't care. You just told me to learn this. Which, fair. So it has to do with enones. So this functional group here is a compound functional group where there's resonance between all four of these atoms, so it reacts as one big thing. And we call it an enone because it has an alkene and a ketone all together, so an enone. Now on enones, there are two electrophilic spots, two spots that we could attack. If we number it from 1, 2, 3, 4, with 1 starting at the oxygen, we would call the first electrophilic site the 1,2 site of attack, or the 1,2 addition spot. And then we would call the other one the 1,4 addition spot. And this one's also sometimes called conjugate addition. There's also this terminology that I don't think Tim used, but I just including it here as an FYI because it can show up on MCAT and things. I want you to at least have heard it before. We say nucleophiles that add at the 1,2 position are called hard nucleophiles, and nucleophiles that add at the 1,4 position are soft nucleophiles. Again, we don't test that, but just FYI for future studying. So let's look at our organometallic reagents and see what happens if we add them to an enone. So first up, if we do a Grignard, if we do the RMGBr ET2O with an H+ workup, the Grignard is going to be unselective when it reacts with an enone. We are going to form both 1,2 and 1,4 addition product if we've added it at the 2 position and the 4 position. And if we are doing our synthesis thing and trying to, like Da Vinci robot, make a specific molecule, this is not going to cut it. We want to only get one product a lot of the times. Now, for a normal ketone or aldehyde that's non-enone, Grignard works great. It's super common. But it's not going to be a good option here for the enone. Okay. Then, if we only wanted to get the 1,2 addition product, that is what we would use the organolithium for. So RLi, ET2O, H+ workup. And so the organolithium will only add 1,2. And then for only getting 1,4, this is when we use the, quote, Gilman reaction, which there are a couple ways to write it. I'm going to write it my preferred way, and then I'll write it the other way. So we could write it as R2, CuLi, and diethyl ether, and 2 H+ workup. The other way of writing this is you could write RLi and CuX, where X is a halogen. So you would want to write like CuBr or something. You wouldn't actually want to write the X in the specific reaction. I like writing it this way because it's more compact. It's just writing one thing. And also this is the way all the answer keys write it, and so I think it's just easier to kind of learn it that way. But the structure of it is this little complex. You would have copper with 2 R's on it, and then it has negative, and then a positive lithium. So R2CuLi. This is what is formed when you mix these two together. So either one is fine for putting it there. This whole reaction is called the Gilman reaction. Yeah. So the halogen needs to be there with the copper to start off the reaction, but then it pops off.
Oh,
Yeah. Exactly, yeah. So This is called the Gilman reaction. And this will only add at the 1,4 position. Now, one thing that throws off students is they see this subscript 2 and they're like, oh my gosh, double addition? No, 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 no. If I wanted to add just a phenyl group here, I would write this as pH2 CuLi, and it only adds one phenyl group and it adds it to the 1,4 position. Same thing for if I have an ethyl Et2 CuLi. It's just how we write it. It's just the complex that's formed. Now, we call this kind of family of reagents organocuprates, cuprate because it has copper. And these are much less reactive than the Grignard or the alkylithium. So these will only react with enones, and they will not react with ketones, aldehydes, or esters. This one also you are not responsible for a mechanism for. You only need to be able to use this line reaction. So this would only be like a box problem or a synthesis kind of question. But this is why we have the different flavors of them, because they react differently with enones. And that's why we have several reactions that accomplish very similar goals.
So for the synthesis question, do you not have to write the full Cordero?
Oh, yeah, absolutely, no. Didn't you see the little, like, yuck emoji? Don't draw curved arrows.
Oh.
Yeah, this is truly just line reactions. All of these. You're just doing a lot of line reactions. If you draw curved arrows, like, I was going to say an angel doesn't get their wings, or like a puppy is sad somewhere. But mostly it's just I look at the exam and I do a big sigh. Because normally if someone's drawing curved arrows on a synthesis, they did not do well. So, synthesis questions are basically glorified line reactions. Yeah. Cool. Now, you are not responsible for this mechanism, but you do need to know generally the mechanism for that conjugate, like 1,4 addition. So, the example that Tim gave in class is the thiolate addition. So, a thiolate is what we call something of the form like Rs minus. That is a thiolate. And here, thiolates, or just broadly, thiolates add 1,4. They're a soft nucleophile. So I'm going to go through the mechanism with y'all real quick. So it's going to attack at that 1,4 position, and then we push all the way up to the carbonyl. Okay, so we've gotten to this intermediate structure. What do we need to do to go from this to this? Sorry? Well, we will definitely push this down, but maybe specifically look at this carbon and this. Yeah, so here we have 2 hydrogens. Here we only have 1. So we need to do this kind of weird protonation where we push down, form a double bond, and then use this kind of alkene double bond to go and grab a hydrogen. And here, we're grabbing the hydrogen from this ethanol. So this is a case where the solvent is kind of playing a role in the reaction of doing this general like acid-base step, whereas the diethyl ether solvent doesn't appear at all. Here's one where the solvent does appear. And then that gets us there. This is a special type of protonation called an alpha protonation. You don't need to know that name, but it will come back later. You will see it again, I think, particularly in like lecture 10, so way at the end. But it is just a different type of protonation. Yeah.
Why didn't you immediately grab the hydrogen with the double bond between the carbons instead of pushing the double bond to a different place and then pushing oxygen?
So it's because resonance is happening. Because there is resonance between this and this, you need to show that this is going to form its most stable resonance structure, which would be putting the negative on oxygen. If you had this just go and grab a proton, first of all, like this is an intermediate that is isolated, so we know that that is an intermediate that is formed separately. And second of all, it's kind of just like unlikely for 3 molecules to all line up at the same time to do this reaction in the right order. Because again, these molecules are just bumping around and kind of colliding into each other and reacting. And so that's a lot more chance for 3 molecules to bump into each other than just 2. Yeah. Cool. So I have some practice here. These page numbers are incorrect because I didn't have enough time to like update this with this year's page numbers and everything. So you can either find it in your problem set, I'm sure it's in there, or you can just use the ones on the section sheet. And I want you to try this top one as a mechanism, which should be a really straightforward mechanism. And then these bottom like line reactions. I'm going to give you like 4 or 5 minutes to try to work on some of these. And please talk to each other and work together. Abby. Are you Abby? Hi. Ben?
Yes, you know. Who's that?
Who is Ben? I don't even know that there's Ben in this class. Okay. Now I'm like Nicholas, and that's wrong.
So wrong.
I'm gonna. Daniel.
Oh.
Daniel. Sarah Kendall. Damn, Daniel. Okay, that's helpful. Kendall, Georgia, Agadia. Eduardo. Eduardo? Eduardo. Okay, work. Eduardo. Nicole. Isa. Alisar. Angelica, yeah. Don't tell me. Shoot. Okay. Kate. Then Hanu. Hanu? Hanu? Charlie. Damn. Sorry. Oh, so if it's for deep and roundabout, both of them are equal. No, yeah. For traditional deep and roundabout, either one will work. It's only for an email that is specific to the letters. Well, what's the first thing that you think when you see Westwood? Yeah, that's the extreme. So.
Surely this will be. Okay. So, you starting? Is this fine?
Do you have the spots that have like the platform?
Yeah, it gives me like 3 inches, so me and Kendall are the same height.
Wow.
But I'm actually like 5'1".
Wait, are y'all friends outside of this?
Yeah, can you tell?
Wow. Wow. Yeah, I really
No, because Lizzie calls us a couple. Very couple.
Is this Liz?
I'm not.
Oh, yeah, I don't know.
Oh,
I
okay,
don't know them.
yeah.
The only person I've met on the lab side is Emma, and I met for all
Emma
of
is
the.
Lizzie's mom. Lizzie is so funny.
That's
Lizzie is so
You
funny.
really
I
like
think
Lizzie.
you would be best friends with Lizzie.
Liz?
Like Lizzie is funny.
Emma is Lizzie. Oh, yeah, okay.
Yeah. No, I think you and Lizzie.
The lab person I know the most is Tori.
I don't know.
And I'm making it for her. She was the head chef last year, the last 2 years.
Right, that's like
But Lizzie, tell her hi for me.
Like Cole.
Like,
Y'all's
this is
personalities,
not-
y'all's personalities are like the exact same.
Well,
Yeah, you're right. We're on the same.
I hope that Adidas Invitational.
Oh, this is my uncle's.
Oh,
It's
that's
not
so
mine.
I understand what this
I was like, okay.
Thank you, I found it in my house.
So we have to do what's it called as an arrow.
Oh, we
yeah, I was like,
Like, what is this
think
girl
it's like
doing?
breaking. I don't know, you can
Oh my god. Okay.
So the main one, and it's not my favorite. Like, I don't think that it's great, but it does the job in the same way that contact related is called the organic distributor. Which again, everyone knows that.
Gosh, I'm very track guy.
There's also the test
I
video
love
explains. Crash course has open videos, but I'm just not very interested in they're very kind of general. Those are the ones I know just off the bat. But we can like talk afterwards to like, yeah.
I have a question. Do you anticipate like, how does the entire stand be like, is the real stand gonna be like the same type of songs and the exact same people?
Yeah, those two were literally the exams of the last 2 years, and to make the exam for this year, we like clear out the question from the last year and put a different molecule.
So it's like not, like no jump scares.
No jump scares.
Okay.
Yeah. And if there is a jump scare, I'll tell you in the exam review. Yeah. Okay. The mechanism here should be the really straightforward. Bada bing, bada bang. This is literally exactly the same arrows that are right here. No, nothing new. So for this box problem, what functional group is this? Ester. What's the first thing that you should think when you see ester? Double addition to esters. Now, do you see anything that looks like it was added twice? A methyl. So let's do methyl lithium, or you could do methyl MGBr. In this case, either one works. And ET2O and H plus workup. Done. Donezo. Again, we don't have to do the full mechanism. We don't have to explain it. We just know that these reagents do double addition to esters. And this is the thing we added twice, so we're good to go. Okay, here we have an enone, and it looks like we've added things to the 1, 2, and 1, 4 position. So what did we add at the 1, 2 position? The main thing we added was the ethanol. So this alcohol, this oxygen, was this oxygen over here that was the carbonyl. So she just kind of changed a little bit. She wasn't fully added. And what do we add at the 1, 4 position? A little phenol. Yeah. So okay, what flavor of organometallic should we use to add 1, 2? Granular lithium or copper? Lithium. And what flavor should we use to add 1, 4? The Gilman, the copper. So the question here then becomes, which do we do first? Do we do the 1, 4 addition or 1, 2 addition first? Let's just try doing the 1, 2 addition first and see what happens. So I would do, okay, my ethyl, I need to make lithium, so ETLI, ET2O, H plus workup. So if I did steps 1 and 2 here, what I would get after that addition, so I would have an OH and an ET. And then is this an enone anymore? No. Is this a carbonyl anymore? No, this is just an alkene, and we don't know how those react yet. So that tells us that we can't react with the 1, 2 position first. So I'm going to put that up here in red. I'm going to move these down to step 3 and 4. And then for 1 and 2, I'm going to do the 1, 4 addition first. So we're adding a pH, so it's pH2CuLi, ET2O, and H plus workup. So that means after steps 1 and 2, we're going to get an intermediate that looks like this. And then steps 3 and 4, we now still have a carbonyl that we can react with, that then we can do this alkylithium too. Cool. Okay, bottom one's kind of weird. What functional groups do we have present here? Arine and ether and an alkyl halide. Yeah. So do we know any reactions of ethers? No, we know like diethyl ether as a solvent, but that's not a reaction involving the ether. And really, we don't know any arine ones yet. So alkyl halide, do we know any reactions connected to alkyl halide?
Yes.
Ba-ba-ba. So we can turn it into a Grignard or an alkylithium. That's the only option that we have here. So let's just turn it into one of them and see what we are at. So I'm going to do the Mg0 Et2O, and then this thing is going to become MgBr. Okay. So now we need to get from this is a Grignard reagent, to this. And what functional groups do Grignards normally attack? Carbonyl, like ketones or aldehydes, right? So this means that in this step 2, we have to supply a ketone or an aldehyde. And that's kind of weird, because normally we put the ketone or aldehyde over here and we put the Grignard thing over here on the arrow. But this is just introducing you to the idea that we could have the Grignard thing over here and then put the ketone or aldehyde on the arrow. That's also the same thing. So let's look at the product to try to figure out what we added. So was this OH here initially? No. Was this carbon here initially? No. So we know that we've added that carbon. That carbon has 2 hydrogens on it, and it has an O, and we need it to be a carbonyl. So let's just make a double bond there. And let's see if this works. So I would write that out as the carbonyl here. And here we still need diethyl ether as a solvent. But if I add in this is going to do an attack here. And here, what we wind up with is just a proton away from the correct answer. So we know that with an acid workup, we get to the right product. So again, that's going to be a harder type of question to answer with like trying to think backwards, and you have to having to supply an organic molecule. That's a harder challenge. We are pretty much at time. Would you allow me to do like a 3-minute hydrides overview? It'll be really quick.
Yeah.
Oh my gosh. So the other family that we haven't talked about yet are the hydride equivalent reactions. The purpose of these reactions is to reduce a carbonyl compound to an alcohol. And we do that by adding a hydride, which is a hydrogen with its electrons. So why do we not just use acid or NaH to do this? Well, NaH is a strong base, but poor nucleophile. And H+ is only a single proton with no electrons, so it's not going to be a nucleophile doing an attack of a carbonyl or something like that. So just like we had the carbanion equivalents, we need something that's kind of equivalent to a hydride equivalent. And we are going to use these compounds with boron and aluminum. In these boron aluminum compounds, let's say this is aluminum here, this is hydrogen. Aluminum has an electronegativity of 1.61, and hydrogen is 2.2. So which side's more electronegative? The hydrogen. And so again, it's like an H-. So that's how it's going to attack. We have 2 flavors. One is lithium aluminum hydride, and the other one's sodium borohydride. And they have some differences to them, but let's focus on what's similar for now. So both of them are just going to add a hydrogen. They both have the same exact mechanism of the sigma bond here is where your arrow starts, and you push up, and then you just neutralize it with some sort of acid, or in this case, you can use methanol, HOMe. And this is a case where the solvent is used in the reaction for this sodium borohydride. Again, that's kind of unlike the diethyl ether, which doesn't do anything in terms of the mechanism. So again, these accomplish a similar goal, so why do we have two different versions? Well, let's do a little compare and contrast, and I use a little metaphor for them. So I call lithium aluminum hydride toxic masculinity. So lithium aluminum hydride is very strong, very reactive. It will react with ketones, aldehydes, esters, and even more functional groups that you don't even know about yet. So lithium aluminum hydride reacts with everything, very reactive. And because it's reactive, we have to keep it in 2 steps. It can't be around this H plus workup because otherwise it would just react with the H plus workup molecule rather than do what we want it to do. So that's why it has to be 2 steps. And then this is all contrasted with sodium borohydride, which I describe as soft boy. So soft boy, very mild, weak, only reacting with ketones and aldehydes. Because it's mild and weak, we can do it in one pot, 1-step reaction with methanol. And it's not going to just go after the methanol and attack it. So it's because it's mild that it can do that. And then we also have the enone question for both of these. So neither of them are selective, 1,2 versus 1,4. Both of them are just going to give a mixture of the products, which is horrible, unless we use our little Uno reverse card of CeCl3. So if you sprinkle in CeCl3 into the sodium borohydride reaction for an enone, it will only add 1,2. Whereas if you do not have the CeCl3, you're going to get a mixture of the 1,2 and 1,4 addition. I know that was rapid, but this is mostly just kind of a summary tool for you to look at. There's also the reversible carbonyl additions, which I've kind of grouped as base and acid catalyzed. This is for you when you're studying, but we've already done a lot of this when we did the acetal reaction. So, with that, thank you for coming to section. The practice exams, if you haven't grabbed them, the printed copies are in the back by Charlie. And I'll stick around to answer questions, but have a good weekend. Yeah. Scrolling. Yeah, totally. Yeah. Yes. Okay.
My question is back to that one, this one. I'm not sure how you determine which one was first or second,
Oh.
which one.
So we talked about if we did the 1,2 addition first,
Yeah.
we would form this, right?
Yeah.
Now, does this have a carbonyl anymore?
No.
Does it have an enone anymore?
No.
No, so it's not going to do any of the reactions that we've talked about up here because it doesn't have a carbonyl or
So
enone.
it's really like a guessing check type of thing.
Well, we're doing a guess check here, but now that you've seen it, you
Oh,
always
now I
know,
know.
react with the 1,4 first.
Oh, okay.
Yeah.
All right. Thanks so much.
Totally. Yes.
Do you have
Yeah.
advice for me? Because I've never been good at learning. I've been good at memorizing and studying and then forgetting afterwards.
Heard.
And I actually want to learn this because I feel like I would need this for like the DOT and
Yeah.
dental school and everything. What do I do? Like I picked the hardest class to like start learning.
Well, I feel like that characterization also like undercuts the learning that you have done up until this point. But like, I think everyone's kind of process of learning is so different, and I think a lot of it's figuring out what doesn't work for you. So like when I did my first Oakham class, the thing I realized doesn't work for me. This is not the advice I'm giving. The thing that didn't work for me was the lectures. The lectures were horrible, and I was just like, I would be better off reading the textbook. And so I like stopped attending lectures for that class and just read the textbook, and that was better. But really, the thing that helped me the most was working through the Oakham as a second language books, because they break Oh my gosh, words. They break it down into really small skills to practice
Okay.
and to build up your confidence on those skills. Because to answer these types of questions, you have to put a lot of different skills together. And so if I were you, I would turn to the Outcomes of the Second Language books. Now, do you remember from the first section, the like concordance table? Okay, work. I would look there and try to work through that section. I think it's in the second semester book. But they will kind of talk you through beat by beat.
And I should be doing that as I'm doing the PSAT. and
Yes.
stuff. Okay.
Yeah. It's a lot. Like, learning broadly is a hard thing. But again, no one in this class would be here if they couldn't do it. Like, I know you can. Yeah.
I like your confidence in me.
No, yeah.
Bye-bye.
Bye.